basically this is a version of successful approximation. It has all the same interpretations as the deterministic case. There's really no difference at all. And I talked about how it's used in analysis. So one big use of value iteration is to reveal structure of value functions and policies. And I gave one simple example, this is inventory model. So the inventory model just think of it as a linear system. It doesn't even matter. So I've basically got a linear system. Who cares about the interpretation in a sense? We talked about it last time. But the main thing is its linearity and cost function, which is convex. And what we find is that the value iteration algorithm preserves convexity. So if V0 is convex, so it's Vn for each n. So that gives you structure of 8 star. So 8 star turns out to be convex. Because basically you can choose an initialization such as 0. Take V0 to be 0, that's a convex function. So you'll find out that V1, V2, V3 are convex. And under assuming that the value iteration algorithm converges, and we can talk about mild conditions under which this is the case, under which convergence is. But this will hold under very, very general conditions. So these are convex functions converging to a limiting function. It must be convex as well. So I gave you the idea of the proof, and I just saw I only had 5 more minutes, and I just want to make sure you all understand it. So convexity, we want to show I had an inductive proof. Assume Vn is convex. You have 2 initial states and 2 initial controls that are arbitrary. Right? And I mentioned this idea of using coupling. And this is really the crucial part. So the first time I saw this, as an assistant professor, I was blown away. The fact that using the actual sample path description is the only way to go. If you don't do it if you don't think about terms of sample paths, keeping the same noise, with 2 different initial conditions, then you don't get a proof. So I don't know how to prove convexity without this coupling argument. But the coupling means I'm using the same noise, even though they're 2 initial conditions. Now you might think, you might not have done that. You might have put an I here too, where the SIs were independent, and that might have been useful for proving something else. But here, the coupling of the noise is crucial. So this is notation I'll use throughout. And it confused some of you. Okay, so whenever I talk about a convex combination, that's the definition of a convex combination. Some of you asked me this after the lecture. That theta is between 0 and 1. So I want to be able to show that that's convexity. That the value function at the intermediate point is less than or equal to a convex combination of the value functions. And can we do this many lines? I think maybe we can. All right, so Vn plus 1 of x theta, it's equal to the min, and the min is less than or equal to plugging in any arbitrary value. Voila. And, when I write down PUVN, that's a conditional expectation, or one step in the future. And this is the expectation given the particular, I guess I should write down the expectation. I'll leave out the theta for a second, okay? I'll leave it out, okay? You can erase that. Erase the theta momentarily. Okay? So the definition of PU Vn of x is the conditional expectation one step in the future, given u. I'm taking a particular u, arbitrary really, and x theta is the x that I'm interested in. Okay, so this is I'm getting inequality because instead of a min, I'm sticking in u theta, just basically arbitrary value. Okay. Now this is equal to right? I'm using this convention throughout. When I write a super theta, I mean a convex combination. So if I look at a convex combination, of x, take t equals 0 of x1, it's going to be a convex combination of everything over here. Right? I mean, I just hate to waste ink. So I had the I there. You don't have to change it. I put it in a different color. So it's true for I equals 0, 1. It's also true for theta. Okay, because of the fact that you take it's a linear system. So I take linear combinations. All right, it's a bit of algebra there. Homework problem for you all. I just don't think it's worth just writing it out like that. All right, so now we use convexity. All right, I used convexity twice. C was convex, so C of x theta u theta is less than or equal to 1 minus theta, C of x 0 u 0 plus theta times C of x 1 u 1. That's convexity of C. So right here I'm using convexity of C. And over here, I took this and I said it's less than or equal to 1 minus theta times this plus theta times this. That's convexity via. All right? Done. Almost. All right, so what do we get? We get that this is equal to we'll keep it as less than equal to 5, right? Rewrite this. Now again, I'm writing down the definitions. This expectation, x0 had the initial condition, x0 of 1 had the initial condition x0, and the control input u0. This expectation is nothing but that. That's my weird notation. The only thing hard about here is notation. That is equal to that. Okay? Now here's the thing. This is true for any u0 and u1. So if I have something less than a function of u0 and u1, I can now take the minimum of the right-hand side. Take the minimum over all u0 over here, take the minimum over all u1 over here. There's nothing, if something is, I've got something less than this for all u0 and u1. So take the minimum. When I take the minimum of this over all u0, what do I get? I get vn plus 1. The minimum of this over all possible u0 is nothing more than vn plus 1 of x0. The definition. So it's all notation, There's one brilliant trick of coupling. That's really it. And after that, it's notation, notation, notation. So you can see that any linear system with convex cost, you can play out the same game. You're going to get a convex value function. So and the convexity gives you structure. So in this inventory model, it tells you there's a threshold policy. That basically you ramp up inventory as fast as you can until you get to the threshold, and then you back off. And you'll prove that in the homework. I just don't want to waste our time with that. It's pretty quick. And with two-dimensional models, it applies switching curves. You get a lot of structure of the policy. And that structure then simplifies a search in approximation. Questions? You're happy? You look happier than normal. All right, so I know the one thing I got that confused most of you is that, and I just urge you, if you don't understand it, I've been saying this every day since lecture 1, you're going to have to learn this or you can't pass the course. That this means conditional expectation. And that's a conditional expectation because the initial condition and the initial control are given. The initial condition here is x0 and the initial control is u0. So that's it. You just couldn't possibly pass this course unless you learn that this is equal to this. And so that's not going to explain it again. Okay. All right. Can I kill it? Questions? Okay. So, this is an algorithm that maybe wouldn't even have been taught in courses in stochastic control because it's so complex. And I taught it because I love the math so much. It's such a pretty algorithm. But now there's a new motivation. The main motivation is that it's the most convenient way, approach of plugging in to reinforcement learning algorithms. So it's the engineering motivation is approximate dynamic programming. So you have to be patient for this. It's not until November that you'll know what I'm talking about. But it turns out this is you can approximate policy equation using these techniques, and it's the nicest way to go. Besides that, we'll see. I'll show you why it's hard to code. But let's remember what it is. So I've got the average cost optimality equation is 8 star equals T of 8 star. And that was equal to, let's remind ourselves. And that was we're making the convention that 8 star is 0 is 8 star. So we're just normalizing without loss of generality. So that's the thing about the average cost optimality equation. I can always add a constant 8 star and preserve the equation. So 8 star is not unique. By freezing this, at least for finite state space, I can ensure it's unique. All right, so now, this is matrix vector multiplication. That's a linear function. The minimum of linear functions is concave. There's a concave function. T is a concave function. Yeah, as h gets larger and larger and larger, this would blow up, but so would this. So it's hard to tell whether this, in some sense, is increasing or decreasing. So let's just forget about that. It's concave. We're looking for a solution of 8 star equals T of 8 star, and so I look at the line. The line where T of H equals 8 star, where the y-axis equals the x-axis. Okay. Now I know H is a vector. Okay, for a finite state space, for a state space of size n, H is a vector of size n. So drawing a curve like this, I know it's of course, if there were 2 states, it would be a two-dimensional surface, and I can't visualize it in higher dimensions. Okay, so H is not a scalar. It's just this is the essence of concavity means this in 1 dimension, and it means something like that in 2 dimensions. All right. So Newton-Raphson. As I said before, if you look at approximation, and What's the notation I use? I used an A. So T maps functions to functions, which and functions are considered column vectors. So its gradient would be a matrix, you know, and so this is a linear approximation of T. Now, if there's only a finite number of controls, this is a finite minimization, T might really have corners. It might be piecewise linear. You know? So this might not be differentiable. You know? But we can still sort of look at affine approximation.